plus T2 plus T3 to C infinity is what we call the connection in what? In a series, in a parallel connection. Alright, this one is in series, while this one is what? Is in parallel. Alright, that's the first thing we need to take note of in what? In capacitor. Don't forget that we said that capacitor is defined as a device, right, we use in storing electrical charges. And I've stated it all from the capacitors to the capacitor what we have, and that's what we are using to derive the series and parallel connection of that. So that is that. Now there are also several things I want to talk about, alright, like what you have as the capacitance of different shapes. Okay, there are shapes that we consider in physics, alright, that has capacitance in advanced level. Okay, now before that, there's what we call a parallel plate capacitor. Parallel plate capacitor. Parallel plate capacitor. Now, in parallel plate capacitor, there's a formula I'm going to give us, alright, so that anytime you see, you can always apply them. Meanwhile, the factors that affect capacitance of a capacitor, we have area. Area affects the area of the plate, alright. We have the separation distance between the plates, and we have the dielectric, alright. Those are the three terminologies that affect, alright, that affect capacitance of a capacitor. Factors affecting capacitance of a capacitor. We have number one, like I said, number one, we have area of the plate. Number two, alright, we have the distance, okay, or you can write it as separation distance between the plate. We have separation distance between the plate. And the last, we have number three, we have dielectric, right? Dielectric. So for the first one, for my area, my capacitance is directly proportional to the area, then my capacitance is inverse proportional to the distance. Okay, so that is how to go about that. So before we move to the different shapes of capacitance, all right, or the termination of capacitance for different shape, there's something I'm going to like to talk about. Then thereafter, I'll just show us how to find the capacitance of a different shape. Alright, so once we have seen all of that, okay, so there's something I want to show us. So I said that these are the factors that affect what? That affect the capacitance of the capacitor, area of the plate, the separation distance between the plate, and the dielectric. So for the first one, your C is directly proportional to A. Alright, capacitance is directly proportional to the area of the plate. It suggests that if as capacitance is increasing, area is also increasing. Alright, when capacitance is increasing, area is as well increasing. Then this one, alright, which is the separation distance, we see is inverse proportional to 1 over distance, alright, between the plates. It suggests that as capacitance is decreasing, alright, distance is what is increasing, or capacitance increasing, distance is decreasing. Alright, so one is increasing, the other is increasing for the first, which is C proportional to A, while the second, capacitance is what is increasing, and the distance is what is decreasing. Or you can say distance is increasing, capacitance is what is it called? Is decreasing, then distance is increasing. So any of the two, one is increasing, then the other is decreasing. That is basically what it is. So for that, alright, there is what we call parallel plate capacitor. Alright, I've mentioned mica, I've mentioned paper. Alright, there's what we call parallel plate capacitor. So what is a parallel plate capacitor? Parallel plate capacitor. So for the parallel plate capacitor, alright, we have two charges here. Alright, so we have Q, alright, charge Q, positive and negative direction. Alright, and your parallel plate capacitor, there's what we call the distance between the two plates. Okay, D. Alright, so you have in between this place, you have D distance in between the two plates. Alright, you have the potential V. Alright, so you have D here. Alright, then you have V here. So now if you use what we call Gauss theorem, in electrostatics, Gauss theorem, alright, you must have heard that before. Gauss theorem in electrostatics or static electricity. What's going to happen is that we are going to be having our value of parallel plate capacitor, alright, because the intention is to derive the value of C is equal to EA over D. Okay, so what is our electric field intensity in electrostatics? Alright, of course we know that our E is equal to voltage over distance apart, all right, in equation 1. This is what we call what? Of course, the first value of electric density is F is equal to E is equal to force over charge, all right. Force per unit charge is what we call electric intensity. But in the concept here, loss, all right, E is also V over D because it has many formulas. So electric intensity is equal to voltage over distance apart. So if that's the case, now let us look at the other value of E, all right. Another value of E, all right, electric intensity I can give you is also that the value of E is equal to charge density over Epsilon. What is charge density? Charge density is equal to Q, is sigma. Sigma is equal to Q over A, all right. And the other value is what? You know, I told us that we have many values for electric intensity. We have voltage over distance apart. You can use to determine electric intensity. In electrostatics, you can use sigma, which is charge density over area. You can also use E is equal to voltage over distance apart. So use those three formulas to determine the value of the electric intensity. So if that's the case, so I'm going to be writing E, this sigma, okay, sigma, this sigma, and that sigma is what we call the charge density. Sigma, don't forget, it's called charge density. Okay, so for that now, what's going to happen is that I'm going to be having electric intensity is equal to, anywhere I see charge density is equal to Q over A. So I'm going to be having Q over area, all right? That's how this thing. So we have charge density over Epsilon rather, not over area. Charge density over Epsilon over permittivity. Okay, charge density over permittivity. Charge density is equal to quantity of charge over area, while electric intensity is charge density over Epsilon. Okay, so if that is the case, I'm going to be having E. Your sigma is now Q over A, then over another value of Epsilon. Don't forget that your electric density is charge density over Epsilon, and Epsilon is called the permittivity. Okay, permittivity. So this is what we have. E is equal to Q over A over Epsilon. Alright, then E is supposed to be Q over A, then Epsilon. Alright, that's what we have as the electric intensity in terms of charge, the area, and the permittivity. So if Epsilon is, if E is equal to Q over AE, then what is your E? We said from equation, let's say this equation 2. From equation 1, we said E is equal to V over distance apart. Then your E is now V over distance apart is equal to Q over AE. Alright? So now, or we can also rearrange it. If you arrange, it's also Q over A is equal to V over D. Then what is Q? Q is equal to CV. So you have voltage over distance apart is equal to, anywhere you see Q, write what? CV over what? A, then permittivity. So our V can go with V if you cross multiply. Okay, so you have V over D. Okay, V over D is equal to CV over A Epsilon. So you do something of this nature. Alright, so this one is coming to this. So you have A Epsilon V is equal to CVD. Alright, so A Epsilon V is equal to CVD. We suggest that V go with V. Then we'll have A Epsilon is equal to CD. Alright, if A Epsilon is equal to CD, alright, let us make C the set of the formula. So you have A Epsilon is equal to CD. Epsilon is permittivity, then divided by D over D. Alright, so you have A Epsilon over D is equal to dCD over D. This one has cancelled. Then you have A Epsilon over D is equal to C, or C is equal to A Epsilon over D. This capacitance in terms of the area, the permittivity, and the distance apart. That is why we said that our capacitance is directly proportional to the area and the same value proportional to the